last time we have solved this example. I have explained design of the purlin, and this was example number. Yes, this example we solved. And actually, in this example, we were not specified that how many sag rods we need to use. So I told you that when we solve this example, so the decision regarding the number of sag rod is taken depending upon the angle or inclination of roofing system. So, and I have told you that we have already discussed this here. So number of these sag rod that we need to use in our purlin design is depending upon inclination of top chord or inclination of our truss. So if inclination is less than 15 degree, we have to design the purlin without any sag rod. And if the inclination is between 16 to 25 degree, so we start the design by considering one sag rod. And if the inclination of truss or the top chord of truss is more than 25 degree, so we always start the design by using or assuming two sag rods. So this will not be maybe given in the problem or in examination that how many sag rods you need to flat. So you need to uh, decide number of the sag rod depending upon inclination of roofing system. So sometimes it may directly be specified regardless that what is the inclination. For example, in this example, so this just I will quickly cover this example just to give you the overview what we have done in the last time. So this is same problem, example number 7.2, but a different. So last time we solved this example. Last time actually we solved the same problem 7.2, but the number of the sag rods were not given. So our inclination of truss it was 30 degree. So we decided two sag rods. So we completed this design by using two sag rods. But if the architecture or maybe it is already being specified that you have to use one sag rod, then what will be the difference in design? So this is just the repetition and just it will also give you the overview of the purlin design. So our data is same, but what is asked in our statement? Design a channel section purlin. So it is also mentioned that we have to design channel with midpoint sag rod. Midpoint sag rod means that we have to use one sag rod that we need to provide in the center in later direction. So as we discussed last time that sag rod will only be used to constrain the bending in y direction or about minor axis. So our design data is the same. We are given the dead load of roofing because purlin they are carrying the load of roof sheeting, insulation panel, and the self weight of purlin. So these loads are directly given in Newton per meter square for distributed load. So dead load of roofing is 160 Newton per meter square. Insulation panel load is given as 50 Newton per meter square, and we are assuming some suitable self weight of purlin. The assumed self weight of the purlin is 100 Newton per meter square, which is approximately 15% of all applied load. Sorry for the interruption. So which is all a live load. This means that if you add 160 with 150, then if you are taking the 15%, actually it is also included the live load also, which is supposed to be 600. So 600 kilogram per meter square multiplied by 9.81 will give us the load in Newton per meter square live load. So inclination of our truss is given as 30 degree. Panel distance is 2.5 meter. Panel distance is the distance between two panel points in horizontal direction. And S is the spacing of truss. So spacing of truss is also equal to length of furlong. And number of trusses panels are 8. So if one panel is having the length 2.5 meters, this means that total length of truss will be 20 meters. 2.5 multiplied by 8. Again, when we are computing the dead load, so we need to convert all type of load into UDL. So UDL, how we can convert? If we are multiplying the load, which is Newton per meter square, with the spacing of furlong. So spacing of the furlong is equal to the panel length, 2.5. So if you multiply load with 2.5, so load will be in Newton per meter. So while computing the dead load, we supposed to keep the all type of the dead load separately and the self weight separately. So here you can see that with bolded, this is a self weight. So although we are also computing the total load, but we are keeping the self weight of the furlong separately and other type of the applied load or other dead load separately. Why? Because self weight is acting at the centroid of the section. So it will only produce bending moment and no torsion. But all the other load, whether they are live load or dead load, they are also producing the torsion along with bending moment. We have already discussed. So total dead load will be 525 plus 250. 250 is the self weight and 525 is the superimposed dead load. Similarly, the live load, which is we are given 590, if the inclination of roofing system is more than 30 degree, then the snow load or the live load will be equal to 590 Newton per meter square or 600 even you may assume. So Newton per meter square multiplied by the panel length or spacing of furlong, so live load is 1475. Total load will be the summation of the live load and dead load. 1475 plus 525 is equal to 2000 plus 250 is the self weight. That is total load. So again, we are keeping the self weight separately. So while we are computing the moment about x-axis, I told you that whether we are using one sag rod, two sag rod, or no sag rod. So sag rod are not constraining the bending about x-axis. So moment about the x-axis is independent of the number of the sag rod, which will be equal to omega L square by 8. So here I told you that how we can compute the moment. So if we are computing the moment about the x-axis, so we need to consider total load. Total load which is including the self weight plus superimposed dead and live load which is 2250. We have to add up. And why we are using cos 30? So cos 30 actually applied load is the incline, but it is not parallel to the web or x-axis of our section. Just like here, because this red line is the gravity load. So if we are resolving this load into two components, one component is acting along x-axis and one component is acting along y-axis. The component of the load which is acting along y-axis is producing the moment about x-axis. And the component of the load which is parallel to x-axis is producing the moment about y-axis. So this is a self weight. Self weight is acting at the center. So self weight or the component of the self weight are only producing the moment about x-axis and y-axis. But the component of the superimposed dead and live load, they are producing both moment and also torsion about the centroid of section. And further, I told you that these charts are available in LRFD manual. So I believe that page number was maybe 99 or 98. I think you can tell me page number 100. So this is a table for mid-span sag rod or for one sag rod. If we are using one sag rod, then our maximum bending moment about x-axis will be same as a omega cos s square by 8. S is the length of our furlong, or you can say omega L square by 8. So what is omega cos theta? So cos theta is the component of load which is along the y-axis, or this is a component of the superimposed or total load which is producing the moment about x-axis. So, but moment about y-axis, so we can consider this is a moment diagram about x-axis. So the maximum moment about x-axis will be omega cos theta into s square by 8. So this is the bending moment diagram if we are using one sag rod about y-axis. So this sag rod will behave as an interior support about y-axis. So our bending moment diagram will be like this. So the maximum bending moment is at the sag rod or at the support point. So moment will be omega sine theta s square by 32. That is the maximum bending moment which is produced about y-axis if we are using one sag rod. And similarly, we can see that what is the total force in one sag rod. The total force in one sag rod is 5 by 8 omega sine theta into s. So these values I have written over here. So if I'm computing the moment about x-axis, I have to use total load, including self-weight, superimposed dead load, and live load. Omega cos theta by 8 into s square is the length of furlong, which is 5.5 equal to, which is equal to spacing of trusses. So mx is the total moment, which is 7,368 Newton into meter about x-axis. About y-axis, I have picked this value, omega sine theta over 32 into s square from the chart, this chart that I have discussed. Okay, here, because I have this total load, so I need to compute the moment about y-axis separately due to self weight 250 and due to all superimposed loads separately. Why? Because this load is only producing the moment about y-axis, but this load is also producing the torsion along with the moment about y-axis. So 2000 superimposed dead load and live load, they will be used as a separately to compute the moment about y-axis. And similarly, we are computing the moment about y-axis separately due to self-weight. So this component is the moment about y-axis due to superimposed load, moment about y-axis due to self-weight only. The total moment will be 1063.5 Newton into meter. So I told you that if we want to design as a channel, so we need to convert my also into the equivalent moment about x-axis. Just to revise this, refresh this, I will need to show this slide. So we need to compute the assumed bending moment about x-axis. And for the case of channel, if we want to design furlong as a channel section, so mx assumed will be equal to mx plus 15 times of my. So here I have computed the mx assumed, which is equal to 23,320 Newton meter square. And we will determine the section modulus required as a moment, which is Newton into meter. We will multiply with 1000 to convert into Newton and millimeter divided by bending strength, which is 0.66 Fy. So section modulus required will be 141.3 into exponent 3. And the minimum, we require some minimum depth to control the deflection, which is equal to span divided by 27.5. Span is equal to the length of the purlin or spacing of trusses, 5.5 multiplied by 1000 to convert into millimeter divided by 27.5. So depth is 200. So we need to select the channel section which may have the depth, nominal depth more than 200 to satisfy deflection. So from section properties table, which are given in LRFD design 8, so we need to select. So this will be our first trial section. So this section, which is C230 into 19.9, this section is having section modulus more than 141.3. So we also need to write section modulus about y-axis. Depth is 229, which is more than the minimum 200. So this will be our first trial section. For the same section, you need to write down the BF value, width of flange and thickness of flange as well, just to check the local buckling. So we will check the applied stresses in this section. So the formula will be mx over sx. We know the total bending moment about x-axis. If we are dividing by the section modulus about the x-axis, so we will have the bending stress due to moment mx. So here we need to write m. This is the my, moment about the y-axis due to applied load, applied dead load and live load excluding self weight. So I told you that this load is also producing the torsion. So we are assuming that torsion stresses are equal to the bending stress produced by the my. So what we may do, we may either consider the half of section modulus about y-axis, or instead of this, you can assume that or instead of this, you can say that 2 is multiplying on the upper side. So you have multiplied my over sy by 2. Why? You have multiplied by 2 because you are considering additional torsion stresses which are produced due to superimposed dead load and live load. But the self weight is not producing any torsion stresses, so we don't need to multiply this my by 2, or we need to divide sy by 2. So that's why self weight is only producing these half stress, and superimposed dead load and live load are producing twice the stress double to consider the torsion stresses about torsion stresses due to self weight and live load. So when we are computing these stresses, so this component mx, we know total bending moment about x-axis divided by section modulus about x-axis, my due to 945 due to superimposed dead load and live load, and 118.2 is the movement about y-axis due to self weight only, which is coming. So if we are adding up all the components, this one and also this, applied stresses are 169.5, which are more than bending strength. What is the allowable stresses? Allowable stresses in this case are equal to 0.66 Fy. 0.06 xy, Fy is equal to 250, so dash stresses are around 165 megapascal. So applied stresses are 169.5, which are more than bending for strength or allowable bending stress. So we need to divide. So we will see another option on the higher side. We will not select any heavy option, just any option which may be the little bit heavier than previous option, but not maybe on the higher side. So these are the trial section may be available 2, trial section available 3. Out of this, we are applying the check on this section. So this section will be satisfied. If we are checking the bending strength, section modulus about x-axis of this section is 185 and section modulus about y-axis is 16.6. Okay, here, when we selected this section, the section modulus of this section about x-axis is 174 and section modulus about y-axis is 15.8. So we will try to select a section which is having more section modulus about y-axis more than 15.8. So when we are selected this section, if we are selecting this, so this section having section modulus even lesser than our previous section, but also it is having section modulus about y-axis more. So it means that it will cause more bending stress about x-axis because lesser is the sx value, more will be this component. So we are not going to apply checks on this option. Rather, we will check this option because this section is having sx value and sy value more than our previous trial section. So when we check the bending stresses, the bending stresses are coming 160.84, which are less than 165. So this section is okay. We just need to apply the other checks. Local buckling BF over TF value for the channel, which is 63 divided by 10.5, which is 6, it is less than 10.8. So no chance of local buckling. So final section will be this one, and we need to check the self weight also. So what is 22? 22 is the weight of this section, kilogram per meter. So this weight is in UDL. So we need to convert this load into load acting per unit area. So if we are multiplying this load or the actual cell weight, or you can, what you can do, you can convert actual cell weight into kilogram per meter, or you can convert this load into load acting per unit area. So actual cell weight of the purlin is 22. If you are multiplying with 9.81, so 9.81 is the to convert into Newton. So 10. So 10 is the total length on the one side because total truss length is equal to 20 meter. And number of the panel on the one side are 4. So this thing supposed to be this n value is number of the purlin on one side which are equal to half length, which is 2.5 into 4 divided by total length of truss. Or what you can do, if you know this total weight, which is 222 kilograms actual weight, so what you may do, you can also compare by another way. This is the weight of the purlin, 100 Newton per meter square, total load of the purlin, which is on the total length. So 100, so how many purlins we are placing? So actually 100 multiplied by total length of the truss divided by 2, then you can convert into UDL load or load acting per unit length. So this is the aerial load. So if you don't want to convert it into the UDL load, what you can do, you can convert the actual weight into the distributed load. So self weight check is also satisfied. Okay, then self weight should be less than 1.2 times of the assumed self weight. Then number of the sag rod. So this force in one sag rod we have taken 5 by 8 into omega sine theta from here. If we are using one sag rod, the force in one sag rod is equal to W sine theta over S. And then last time I have explained to you that, let me find the truss just to explain you. That would be in our previous slides. Lecture. Yes, from here. Actually, we from the chart we have determined the force in the one sag rod. But in one side, if number of purlin are 4, 1, 2, 3, 4. If the number of the purlin are 4, then number of the sag rod will be 3. So total force in the sag rod will be equal to total number of the sag rod that we are using on the one side. So we are taking the force in one sag rod from the charts given in LRFD manual, and we need to multiply with the total number of the sag rod that we are using on one side. So the total number of the sag rod will be 1 minus from the number of purlin. So it means that if on the one side number of the purlin they are 4, 1, 2, 3, 4, then sag rod will be 3, 1 minus then the number of the purlin. So you were here. So that is 4. We are having 5 purlin. Actually, if we are having 4 panel point, you can also have a 4 panel point. So I better write it like 5 minus 1. 5 minus 1 or number of the panels. Again, I will explain from here. 1, 2, 3. If we are having 3 panel on the one side, then we will have the 4 purlin. So number of the sag rod will be equal to number of the panel on one side. You can also say like this. So this is the force in one sag rod multiplied by number of panel on the one side or number of the purlin minus 1. So we are having total force in the sag rod. So actually I told you that this force that we are getting, that is the force in horizontal direction. Horizontal direction means that we are having this force in this direction. The chart is providing us the force in horizontal, maybe in direction number 2. But we need the force in diagonal direction. So the angle between them is the theta. So we are using this relationship. So force in the sag rod or reaction in the sag rod is equal to force in horizontal direction divided by cos theta. Because cos theta is equal to base divided by hypotenuse. So in inclined direction force will be F over cos theta. So force, total force in sag rods will be 17,862. And we are using very simple formula. Area required is equal to reaction divided by allowable stress. So area is equal to pi d square by 4. Because we are supposed to use the solids bar as a steel. So R force is there. Allowable stress is 0.6 Fy. So only unknown is the diameter. Diameter will be is coming out to be 12.31. So we need to round it to the upper side. What will be the upper side? Actually, diameter are always available in following size. So diameter in the markets, they are available in following order: 10, 12, 15, 18, 20, 22, and 25 and so on. So if diameter required is coming out to be 11, then we need to provide the diameter 12. If the diameter coming out to be between 12 to 15, then we need to select the diameter on upper side. If the diameter is coming out to be 16, then we need to provide diameter as a 18. So in the market, the diameter of steel bar or solid bar is available in the following order. Okay, at the moment, if someone is having the question, he can ask me. Anybody is having the question from the Sagra design? So I believe that you have already started the panel load calculation. Okay, let me ask. Anis Malik, are you there? Anis Malik. Anis,
Yes, sir.
can you hear me? Have you computed the panel load calculation? पैनल लोड की कैलकुलेशन आपने कर ली है. Also the purlin design, you need to design purlin, two purlins depending upon your case, one angle section and one as a channel. And then at the end that we will discuss today, design of roof shifting. So when you will submit the report on the day of your examination, midterm exam, so that report must include panel load calculation for your truss, table of forces, which must mention that which member is pure tension, in pure compression, or in stress reversal, and also the Perlin design, depending upon your data. So only two students they have completed their calculation, only Hamza Niaz and Moin Abbas. So let me clear it up. You are expecting at least one question of 10 marks in your examination from our lab portion. So in your midterm exam, you will have at least 10 marks question from the lab portion. That may be including the panel load calculation, Perlin design, or roof sheeting design, or maybe table of forces. So you need to be quick. You need to complete your lab report side by side. So, okay, please, you can remove your raise in hand option. Okay, next is design of roof sheeting, galvanized iron, GI corrugated roof sheeting. So in this design, actually what we want to learn. So for example, first of all, I will show you these pictures. So on the top of purlin, we need to place these corrugated steel sheets or maybe any other type of the roof sheet. So actually, when I talk about the design of roof sheeting, so in our truss system or building, we need to compute at how many number of the sheets are required, what would be the length and the width of each sheet, and what would be the thickness of each sheet. So we need to design what size of the sheet we need to buy or we need to use, and what would be the length of one panel of the sheet, and how many number of the sheets we require just to cover entire roofing system. So we need to provide the roof sheets on both sides. So here you will see that we are having number of sheets panel which are placed in a proper pattern or proper manner to cover up the faces on the both sides. So these are the corrugated steel sheets. So in before the designing, we need to understand some basic terminologies which we may use for the design of roof sheeting. Again, roof sheeting design means that we want to select decide the panel size of one sheet, thickness of the sheet, and total number of the sheets required to cover up the area or the total area of total roofing system. So actually in the market, galvanized iron corrugated roof sheeting, they are sold in a certain designation. So we are given a proper name. So The name is designated as a following. So in their name, we are having two terminologies, two parameters. Number one is the nominal pitch in millimeter and second is nominal depth. So what is the pitch and the depth of any sheet that you will see in the next slide. For example, we are having two sheets which are widely or commonly available in markets. Number one is 65 into 13 GI corrugated sheet. And second type of the sheet available in the market is 75 into 20 GI corrugated sheet. So what this 65 represents? 65 represent that this corrugated sheet is having pitch 65 millimeter and it is having the nominal depth 13 millimeter. Similarly, 75 into 20 GI corrugated sheet means that this is a corrugated sheet which is having pitch 75 and nominal depth as a 20 millimeter. So nominal depth means that actual depth may not be 20, it may be 19 or it may be 21. We will see. Okay, here in this slide, you will see that what is the pitch. So here you will see that from here, this edge to this edge, maybe we are having one corrugated sheet, maybe one, and here we have to show some discontinuity. It means that total width of the sheet may have some more number of the corrugation. So actually, I have written the dimension 19, 585, 75, and 1.5 with reference to 75 into 20 corrugated sheet. But from here, what is the P value? P is the center to center distance between two consecutive trough point or two crest point. So from here to from this crest point to this crest point, this is a pitch, center to center distance, two consecutive or distance between two consecutive trough points. From here to here is the pitch in along the length of the sheet. So that is the P. So pitch of this sheet 75 into 20 into GI mean that the pitch of this sheet will be 75. So that's why I have written here 75. So for GI, so here in maybe I need to mention some here. The sheet that I have used, that is 75 into 20 GI. So this is for this one. And total depth from the lowest point to the highest point. Actual depth is 19, but we are representing as a nominal depth as a 20 millimeter. So all the other terminologies we will discuss in upcoming slides. So for the time being here, I just need to explain that what is the pitch. Pitch is the distance between two consecutive trough points or crest points. And the depth is the distance from the lowest point to the highest point. So one corrugation, one complete corrugation means that distance between two trough or crest point is also called as a one corrugation. So this is the sheet. So this is how we are placing the sheets, one sheet, and then we are placing the sheet on another. So here, these dimensions have nothing to do because these are as per other specification. But I want to just explain that we are having one sheet, and then when we are placing another sheet, so we need to provide some cover on the sides. And similarly, we need to provide the cover along the length. Why I'm explaining this? Because these are important to understand that total area covered by the one sheet. So these are the terminologies. If we are having GI 65 into 13 sheet, then nominal pitch for this sheet is 65, and 75 into 20 mean that nominal pitch of this sheet is 75. Actual pitch may be 76, but nominal pitch is 75. But actual pitch for this sheet is 66, and actual pitch for this sheet is 73. So we always round the actual pitch to the nearest multiple of 5 millimeter. So we are not calling as a 73 into 20, rather we are calling 75. 75 means nominal pitch is 75. 13 is the nominal depth of this sheet, and 20 millimeter is the nominal depth for this sheet. Actual depth of this sheet is 13, but the actual depth of this sheet is 19 millimeter. Similarly, the width of this sheet. In the market, actually these sheets are rolled. So maximum width, the width of all sheets which are available in the market is constant, which is 0.7 meter. 0.7 meter or 700 millimeter. This means that in the market, this is the width. So the width of all the sheet is constant. The width is 700 millimeter, but they may have different length. For example, here, all sheets, they have same width. Width means this dimension, and the length may be variable. The maximum length available in the market for one sheet is 4 meter, and we can cut 4 meter into different sizes. So we can cut along the length maybe in the multiple of 0.25 millimeter, 0.25 meter, but width cannot be increased. So the maximum width of the one sheet is 700 millimeter, and maximum length of the sheet which is available in the market is 4 meter. So it means that if the length of the inclined length between the purlin is more than 4 meter, then we need to use another purlin within the side. We cannot cover the spacing between two purlin if the distance, inclined distance is more than 4 meter. So at the start, we are practicing that we make sure that total inclined length between panel point should be less than 4 meter. And how we will do, I will explain. So total width of the sheet which is available in the market is 700 millimeter. So S is side lap. Side lap is 1.5 time of the corrugation. So side lap is mean that when we are placing two sheets side by side, so we need to provide some overlap so that if during the rainy season water may not percolate along the side. So this side lap is equal to 1.5 times of the pitch or 1.5 times of the corrugation. So 66 multiplied by 1.5, answer is around 105. Similarly, 73 multiplied by 1.5, answer, if we round into the multiple of 5 millimeter, answer is around 115. So what is this side cover? Now I will show you again. So when we are placing, so there is some overlap that we provide at this side. So side is on these sides. So here, this is at the bottom, you can see that we are having one sheet and another sheet we are providing on the top on the other side. So we need to provide the corrugation as a 1.5. Okay, here from here to here we have one corrugation or one pitch, and from here to here we are having half corrugation. Our total side cover from here to here is equal to 1.5 times of the pitch that we must provide, and then we are placing the bolt or the fastener here to connect the bore sheet along the side. You can see here. So these are the connectors. We are also provide the connector or the bolt at the edges and along this length also to connect intermittently at some interval with purlin. So what is this side cover? it is specified as a 1.5 time of the corrugation or 1.5 time of pitch value. So with fastener, we are connecting with the fastener with a maximum spacing of 300 millimeter in perpendicular direction. So we are connecting at a distance of 300 millimeter also. 300 millimeter is around 1 feet. So what I want to say that at the end, we are providing, for example, this is the end of one sheet, this is the other end. We are connecting, and also along the center, we are also connecting with fastener, with the purlin. So at the bottom is purlin here, with the purlin, with at spacing of the fastener around 300 millimeter or less, just like in this slide also. We are connecting at these ends and also along the length with a spacing of the fastener less than or equal to 300 with the purlin. So this fastener is connecting the roof sheet with the purlin. Just like here, we are also connecting the both sheet at the end and also along the width direction with the fastener, and this fastener is attached with the purlin. Cover. Actually, cover is the effective width covered by one sheet. Effective width means that how I will explain. So cover is the distance from center of this side lab to the center of other side lab. So this we are assuming that this is the total effective width covered by one sheet. So just to cover the width of which is equal to 585. Just with total length of the sheet, we are using 700 millimeter. But actually, some of part of the width is used to provide the overlap. It means that if we are subtracting the overlap, then we are having the net width, which is actually the covering the spacing or the gap between purlins and trusses, which is called the cover. So cover is the effective width covered by one sheet. That is the distance from the center of this overlap to the center of this overlap. From the total width, if I subtract half of the cover from the one side lab and half of the side lab from the other side, then we will have this C value. So you can say that C value is equal to, if I will modify here, so this value is equal to total width minus S value. So this will be our cover. This means that a sheet of 700 millimeter is only covering the space of 585, and 585 means 700 minus 115. Let's see from here. 700 minus 105 is 595, and for this 700 minus 115, because S is the side lab. If we are subtracting the side lab from the total width, then that will be 585. So I need to correct here. Yes, it is already correct, 585. So a total sheet of width 700 millimeter is only covering a space of 585, and other 115 millimeter width is used to cover the lab. Similarly, we are providing the sheet, this is along the length, this is along the width, and along the length, we are providing the roof sheet as an incline. So here from this diagram, so I am just showing this length. We are placing one sheet along the length of top chord, perpendicular direction to the purlin, and then other sheet. So first of all, we all will place the sheet like this way. Yes. So first, in the lowest panel, we are placing the sheet like this, and the second sheet is placed on the top, and the third sheet is placed also on the top of second sheet. So we always arrange the sheets like this way. Why? We are not placing this edge at the bottom of this, because if we are placing this arrangement, if during the rain the water is flowing in the downward direction, so it cannot percolate in the gap. But if the order is reversed, the water may percolate. Okay, here you also need to understand how much length is required. So again, let me modify here if you will understand more appropriately. Yes, maybe I need to change the color or not. And theta value I can take from here. Actually, you can see that that is the top part of the roof. I had one diagram that's here. So purlins are placed on the top chord or at the panel point. So one roof sheet is intended to cover the length between these two purlins, which will be inclined. So this length of the roof sheeting will be parallel to the top chord, and we can determine this length by if we know this panel length. So we are provided the panel length is the horizontal distance between two panel points or two consecutive joints with reference to top chord. If we know this p value and we know this theta, we know the length of this top chord or the length of the sheet that can be placed between two purlins along the length in inclined direction. Similarly here, so actually what I want to explain. So P is the distance, center to center distance between two panel points from here to here. This is the horizontal distance. So this P is the horizontal distance between two panel points, or we are given the panel length. So we know this angle, inclination of the top chord, so we can determine this length. So this L is the length from the center of this panel point to the center of the other panel point. So actually, this L will be equal to P over cos theta, because P over L will be equal to cos theta. And if we want to determine the length value, so we need to divide the P by cos theta, then we will have the length. But this length is the distance from this center to the this center. But actually, just like the side lap, we also need to provide some end cover. We have to provide the overlap along the length also, which is referred as E value or end cover. So this end cover is given by the AISC specified that we need to provide the end lap or end cover 200, that should be 200, minimum 200 for the all type of the sheet, which is approximately equal to 8 inch. Minimum end lap in millimeter fastener are to be provided not less than at every third corrugation over pitch over it per line. So we need to connect along the length. Uh, we need to provide the bolt at each 1/3 corrugation. So how we'll explain? We'll see that we just maybe in the next previous slide. So maybe you can say that there is a one sheet and we have placed another sheet. So we have to connect one and we have to provide the bolt after each 1/3 corrugation. 3 corrugation we need to provide the bolt to connect along the end. So actually what I need to explain that if we want to cover a space whose length equal to L between panel point, we need to provide some extra portion. So we need to provide the end lap. Half of the end lap is provided on the one side and half of the end lap is provided on the other side. So it means that this is a distance from this center to the center of this point. So total length of the sheet is half end lap on the one side, E by 2, and half end lap on the other side. So it means that total length of one sheet. So here I'm computing the total length of one sheet LT, or I can just change this value. Length as LS, length of the sheet, which is different from the L. L is the inclined distance between the panel point, but LS is the length of the sheet required to cover the inclined length. It is equal to P over cos theta plus E. So plus E, half P we need to add from the one side and half P we need to add from the other side. Actually, you need to compute this value for the one panel and also for the two panel also. Sometime, what I mean to say, there is a possibility that we may require only one sheet to cover this entire length. If I am computing this distance, so here n represent the number of the panels. So if you are using the n value 1, here you can compute the length required to cover the inclined distance between one panel. And similarly, you can compute this length value by considering the n value equal to 2. N value equal to 2 mean that you can compute that total inclined length covered between two panels. If a total this by considering this n value 2, if this answer is less than 4 meters, it means that one sheet can cover the two panels. So you don't need to use the smaller size of the sheet. The one larger sheet can be covered the two consecutive panels. So while we are solving, so I will explain them again. Further, number of the corrugation. This sheet is having corrugation 9 corrugation, and this size this sheet is having 8 corrugation. Why this sheet is having less corrugation? Because the width of the total sheet, both sheet are 700 millimeter, but only pitch is different. So 700 divided by 65, maybe answer will be around 9, and 700 divided by 75, answer will be 8. So more is the pitch, less will be the number of corrugation. So T is the nominal thickness. So nominal thickness of the sheet, actually this is represented in gauge value. So actually, if the thickness of the sheet is very small, instead of designating the thickness in millimeter, we represent the thickness in the gauge value. So for example, we will discuss after the break, but before the break, let me explain what is the length. I have already explained. Length of one sheet in meter, that may be with the 1.5 meter to 4 meter. So the minimum length of the sheet may be 1.5 meter and the maximum length of the sheet which is available in the market is 4 meter. So length is always computed in a multiple of 0.25 meters in upper side and preferably should be close to the multiple of horizontal panel length P divided by cosine of roofing system, just I have explained. In roof sheeting design, we are also using AST method. So we are using the allowable stress value 0.6 Fy. So we do not want the stress in the sheet exceed 60% of Fy. So allowable stress in these sheets are 0.6 of Fy. And similarly, in order to control the deflection, so the maximum deflection in the sheet should not be span divided by 90. So center point deflection should be less than total span of the sheet. Span of the sheet means length of the sheet divided by 90. So I will here give you the 10 minutes break. Time is 2:09. Okay, let me have the 15 minutes break. So time is here with me is around 10 minutes past 2. So I will resume the lecture at 25 minutes past 2 p.m.
Yes, sir.
Okay, good. Okay, let me check the attendance. Roll number 56. 56. So 56 is not there. 57.
Yes, sir. I'm present की mic का कोई मसला है. 56.
Okay. No problem. Okay. 57. 57. 57.
सर 57 रोल नंबर नहीं है.
अच्छा ठीक हो गया. 58.
I'm present.
Okay. 59.
Present.
60.
Present.
61. 61.
Present.
Okay. 62. 62. 63.
63 present.
Okay. 64. 64.
Present, sir.
65.
Present, sir.
66. 66. 67. Okay. 67. Okay, ठीक, good. 68.
Present.
69.
Present.
70.
70, yes, sir.
Okay, 71. 71 है.
Yes, sir. 71 present.
Okay. 72.
Yes, sir. 72.
73.
Yes, sir. Present. 73.
Okay. 74.
Yes, sir, present.
75. 75. 75. Are you there? अगर आप 75 का माइक खराब है तो मैसेज कर दो मुझे. 76. फिलहाल मैंने एब्सेंट लिखा 75 को।
यस सर 76
77
Yes, sir. 77.
78
Yes, sir.
79
Sir.
okay 80
Yes, sir. 80.
81 82 82 83 84
Yes, sir. 84.
okay 85 86
Sir, 86.
okay 87
Yes, sir. 87.
88
Yes, sir. 88.
89 89 89
Yes, sir. 89.
okay 90 90
Present, sir.
91
90.
91 okay okay 91 92
Present, sir. 92.
okay 93
Present, sir.
94
Yes, sir. 94.
95
Yes, sir. 95.
96 96 97 97 98 99 okay 99 present है 100 100
Yes.
100 आप present हो अच्छा 101 101 102
सर सर आवाज आ रही है?
हाँ जी आ रही 102
Yes, sir. 102.
okay okay good 103
प्रेजेंट सर 103
104
यस सर 104
105 कहाँ तक
सर
रोल
बस
नंबर?
सर 104 तक ही है, उसके बाद कोई रिपीटर वगैरह आई थिंक कुछ हो सकते हैं।
Okay, okay. Any repeater is present? Please, he can open the mic and can let me know. Any repeater? Any repeater which is online, he can respond me regarding his presence. So no repeater is present.
सर 83 थोड़ा लेट हो गया।
हो गई मैंने मार्क कर दी अटेंडेंस आपकी ठीक है कोई इशू नहीं। तो
सर 98 का ना माइक खराब है तो उसने
ठीक
मुझे
है
मैसेज किया 90 सर को बोल दी।
तो बोले उसने वैसे ही मैसेज
पहले भी
किया है
उसकी
कि
मैं
है वो
नहीं सर
ऑनलाइन
उसका
ठीक
पहले
हो
भी
गया
मैं ही बोलता हूँ सर पिछली बार भी
ठीक है
कराया था।
ठीक हो गया 98 मैंने कर दिया। तो मिस परेरा आर यू देयर आर यू प्रेजेंट?
Yes, sir.
So you should-
65.
So I told you that any repeater or any
Sir, I told 65.
Okay, good.
Sir 101.
क्या हो गया बस तुम सोए उठ के आए हो अभी या कह रहे मैं नमाज पढ़ रहा था? ठीक है 101 मार्क कर ली अटेंडेंस यार तुम्हारी।
Okay, sir. Thank you.
Let me resume the lecture. Okay, everyone please mute your mic now. Okay, before the breaks, I was discussing the terminologies pertaining with roof sheet design. Okay, if you will open LRFD manual, I suppose maybe around maybe page number 90, maybe I don't have LRFD manual with me at the moment, but around maybe page number 88 to onwards, you will have some table for different type of the GI sheets. So actually this table, first table, this is for GI 65 into 20, GI 65 into 30 sheet. So in this table, the properties of various sheets is provided. So I suppose to write here maybe should mention the designation also. Okay, you are provided with these two tables. For example, this table is for 75 into 20 GI corrugated sheet. So here, the properties of different or various thickness of sheets is available in this table. So I told you that we are having this type of the sheet available in the market in following thicknesses. So thickness of the largest thickness is 2.753 and the minimum thickness of the sheet which is available in the market is 0.473 millimeter. So this table is for 75 into 20 GI sheets for different thickness of sheets. So I told you that if the thickness is very small, then instead of representing or designating the sheets into millimeter, we refer these sheets into the gauge number. So lesser will be the gauge number, thicker will be the size of the sheet. So these sheets are designated into various gauge size. For example, if I want to buy the sheet, so I will place the order, okay, please give me 20 sheets of 75 into 20, which is having the gauge 20. So gauge 20 means that the thickness of that sheet will be 1.006 because it is very difficult to memorize the thickness in millimeter. So I cannot place the order, okay, please give me the GI 75 into 20 sheet whose thickness is 1.311. So we can forget this thickness easily. So instead of representing the thickness into millimeter, we refer them with another units which are referred as a gauge number. So if the thickness of the element is very small, so instead of using or referring the thickness into millimeter, we refer them as a gauge value. So more will be the gauge value or the gauge number, lesser will be the thickness of sheet. So for example, thickness of gauge 16 sheet is 1.6133. So for example, if we are having gauge 20 sheet, so gauge 20 means that we will have GI 75 into 20 sheet whose thickness will be 1.006 millimeter, and the weight of this sheet is also provided here. So this sheet will have the weight of 91.5 Newton per meter square. So 1 meter square area of this sheet will have the weight of 91.5 Newton per meter square. Similarly, the area of this sheet will be 1099. 1099 means that the area of the one sheet will be 1099 millimeter. So here when we are computing the cross section area, so we are assuming that the sheet is flat. And similarly, this sheet will have the moment of inertia 5.04 into exponent 4 millimeter 4. So, and this sheet will have the section modulus 5.03. So these are the available gauges or the gauge. This sheet is available in different gauges ranging from 12 to 29. And for 65 into 13 GI sheet, this is available in the market in following gauge number. So starting from gauge number 12 to 22. So for example, gauge 20 is having a thickness 1.066 and the weight of this sheet will be 86.7. So this sheet is lighter as compared to the same gauge sheet of 75 into 20 GI. And area, cross-section area will be 1031. So, and moment of inertia will be 1.95 for this sheet and section modulus will be 2.86. So this is the sectional properties table for different or various GI sheets. So we are having two tables for section properties, one for 65 into 13 GI sheet and the second table is for 75 into 20 GI sheet. So we are where the geometric properties are provided for various gauge values. So there are some terminologies that we need to discuss before designing the roof sheeting design. So US standard gauge is officially a weight gauge in ounce per square feet of a flat sheet, but we are converting this weight from ounce per square feet to the Newton per meter. So actually this weight is computed by assuming the sheet is flat. It is not having any calculation for the simplification. The approximate thickness is calculated by using the steel density plus 2.5% allowance for average overrun in area and thicknesses. So it means that if we know the 1 meter square area, so for the 1 meter square area, and we can multiply this area with the density to compute the weight of the sheet, and whatever the weight we are getting, we increase the weight by 2.5. Why we are increasing the weight by 2.5? Just to include the effect of the corrugation, because the area, the weight is computed by assuming the sheet is flat. Smaller gauge always mean more sheet thickness. So more will be the gauge number, lesser will be the thickness of sheet. So maximum actual deflection due to live or UDL load. Actually, whenever we are computing the deflection in our structure member, we will also see in our theory classes, so deflection is always computed due to live load only. We do not compute the deflection, actual deflection is structured due to total load. Why? Because we are assuming that the self weight is carried by the structure themselves. So structure is always having the deflection due to self weight. So extra deflection will be due to the live load only. So in some other reason that actually we provide the negative camber to the structure member. So if due to dead load, the structure becomes straightened and all the additional deflection will be due to the live load only. So for a simply supported sheet, actually the formula is again omega L square by, it is value is 0.013 into omega LP4 into EI. So P is the length of the sheet, or which is equal to the length of the sheet between the panel point. So actually deflection is always computed by assuming the horizontal distance of the sheet. So I will explain over here. Actually, the length of the sheet is the length is the inclined length, but actually the load is acting in the gravity direction. So in the gravity direction, we need to consider the component of this sheet which is perpendicular to the load, or just we need to consider the horizontal component of the length of the sheet. So this span or this panel, this is the effective horizontal distance which is subjected to deflection. So actually one sheet is covering the inclined portion between the purlin. So deflection is always due to the gravity load. So due to the gravity load, we need to consider the horizontal component of this length because deflection is in the gravity direction. So we're supposed to use the p value. Deflection will always be corresponding to length p. So p is the horizontal component of the length. So actual length is the incline. But in the deflection formula, we're supposed to use the p-value because again, if I would draw the load direction, so load is acting in downward direction. So we need to take the component of this sheet which is perpendicular to this load. If load is perpendicular to the sheet, then we're supposed to use the total length of the sheet. So for the deflection calculation, we're supposed to use the panel length. So we always assume that a sheet is simply supported at the panel point, or it is simply supported between two purlins. So span of the sheet will be the length between two purlins, which is equal to the panel length. So if it is simply for a simply supported span, actual deflection is computed by this formula. And these formulas are also available in LRFD design aid. For sheet with one end continuous and other end is free, or the cantilever, you can say that deflection is computed by this formula. For sheet with one end continuous, we are having this formula. Okay, this formula I will discuss in the next slide. Okay, gentlemen, here this is very important slide. You need to understand that how much area is actually covered by one sheet. Actually here, you may assume that just I will show you this surface. So in this surface, you can assume that this is the one sheet. And this sheet is surrounded by the sheet from the all side, maybe one sheet from the upper end, one from the lower, one from the right side, and one from the left side. Or similarly, you can see that this is a sheet. So this sheet is also surrounded by the sheet from the sides and also top from and also from the bottom. So actually, if we are having total width of the sheet and total length of the sheet, but actually this total space covered by one sheet will be less than the total area of the sheet. Why? Because some of the portion of the sheet is used to provide the side cover or side lap, and some of the portion is used to provide the end lap. So it means that we have to check that we have to compute how much cover or spacing is covered by one full sheet. So here I would like to explain from here. So here you assume that yes, just for your clarity, just assume that this is the one sheet that I is supposed to provide here in the center. So if I'm providing the sheet, so these are the other sheets which are providing on the side, and one sheet is provided on the top and one sheet is provided on the bottom. Okay, here you can see this some shaded region. So this shaded region, actually this is the end lab. So we provide the end lab, sorry, this is a side lab that we providing on the side, and similarly we are also providing the end labs. So that sheet that we are providing on the top side and on the bottom side, so we provide some overlap. Similarly, we also provide some overlap on the sides also. So what we are assuming, so total effective cover is this dash line. So this dash line is the center to center distance between the cover. Why center to center cover? Because I am assuming that half of the side cover is provided by this sheet and half of the side cover is provided by this sheet. Similarly, from this side, half of the side cover is provided by this sheet and half of the side cover is provided by this sheet. From the end, half of the end lab, which is E, provided by the sheet on the top side, and half of the end is provided from this side. Similarly, half of this end lab is provided by this sheet and half of the end lab is provided by this sheet. So effective cover provided by one sheet is this dash line. This dash line that I have shown, which is this center to, which is lying along the center of the side lab and end lab. So this total effective width or cover provided by one sheet will be equal to. So what is the, for example, I am computing the effective area provided by one sheet is equal to width into length. So area of the one complete sheet is equal to width multiplied by length. So if we are having a sheet whose width is equal to W and length is equal to L, that is the total area of one sheet. But actual area covered by one sheet is this, the area between this boundary shown by dash line. So if I subtract the area S into L, so S into L means that side lab. So half of the side lab is on this side, half of the side lab is on the other side. So I can consider, if I sum up this S by 2 from the one and S by 2 from the other side, the total extra width which is not covered by this total width is having the width S. And if I multiply by this length value, so I can say that this is the portion which I need to subtract, S into L. Minus S into L is the portion, maybe S by 2 into L from the one side, and I need to subtract S by 2 multiplied by length from the other side. So because this is the area that I need to provide. Similarly, if I have subtracted, then I need to subtract, so is not working properly. Okay, let me mention from here. Similarly, because I have already subtracted this rectangular, so distance, clear distance from this center to this center, actually this is called cover. So what is the cover? So distance from the center of the side lab to the other side is called the cover. So if I multiply this length with the half end cover from the one side plus half end cover from the other side multiplied by this C value, or if I sum up E by 2 from the one side and E by 2 from the other side, which become E multiplied by C value. So I need to subtract this area also. So if I am subtracting this, so then I will have the area between this dash line. So area between this dash line is the actual space or the cover, area covered by one sheet. And the area which is around the boundary, it is the redundant value or the extra sheet area which is used to provide the side lab and the end lab. Okay, now why I have sketched this like this, because I want to derive this expression. So effective area covered by one sheet is equal to the total area of the sheet minus side lap multiplied by length of the sheet minus end lap multiplied by cover. So from here, I can take the length as a common. If I will take the length as a common, so this will become width minus side cover. So if I subtract the side cover from the width, that will become the C value, cover value, just like I have explained also here. So cover is equal to width minus side cover. So that will become C value, W minus S, width minus side cover is equal to only cover. Cover means the total width covered by the sheet. So from here, I can take C as a common again. So that will become length minus E. So length of the sheet minus end cover multiplied by C. So you can maybe derive this expression by yourself, or you can use this expression directly. This is the area of roofing, effective area of the roofing covered by one sheet. So actually the size of the sheet required is more, but actually one sheet is covering this much area. So area of the one sheet maybe you can say that 100 meters square, but actually one sheet is only covering the area by 90 meters square. Or in other words, you can say just to cover the area of 90 meters square, we need a sheet of 100 meters square area, because we need to consider the effect of side cover and end cover. So, for example, if we want to cover a area of 100 meters square, if we are having total area of the roofing 100 meters square, 100 multiplied by exponent 6, because exponent 6 is used to convert the meter into millimeter. So 1 meter is equal to 1000 millimeter, and 1 meter square is equal to exponent 3 multiplied by 2, which is exponent 6 millimeter. So if area that we want to cover is 100 meters square, so if we are dividing it by the area covered by one sheet, then we will have total number of the sheet. Total number of the sheet required to cover the area of 100 meters square. So N is the total number of sheets required to cover the area of 100 meters square. Okay, here next, design of the corrugated sheet. These are the guidelines. Use reference one for the related definition. So we are supposed to use the ASD method for the design of corrugated sheet. In ASD method, we are using the service load. We are adding up all the dead load and live load without being multiplied with any factor of safety. So service load will be used. So strength reduction factor or factor of safety will only be used along with material strength. So factor of safety is 1.67. So we will reduce the or divide the material strength by 1.67. So allowable stress will be 0.66. So we are only using the gravity load combination. So because we are assuming that gravity load combination will be more critical for roof sheet design. Wind load will not be critical. So how to provide the end lap? So the shade that is on the upper side should be at the top. Shade which is at the bottom, it has the end on the lower end, so that when there is a rain, water may not percolate in the gap. So if we are providing the arrangement like this, so if during the raining season, if the water may percolate inside, so overlap is always provided like this way. So according the length of the sheet, panel length is corresponding to 1, 2, or 3 times the inclined panel length plus the required end lap is computed. Okay, here I need to explain. How I will explain this. So I need to explain. Maybe I need to explain from this slide. Let me make the duplicate. Okay, here you may see that we are having 1, 2, 3, 4, and 5 and 6 panel points. So we place the purlin at each panel point, maybe here. Maybe one purlin we may place over here. Maybe one purlin we will place here. One purlin we need to place here. And similarly one purlin. I'm just considering one side. So on the one side, number of the purlin will be equal to number of the panel points. So I just want to explain the placement of sheets. Assume that this might be the sheet that we may place over here. Or I may rotate it more appropriately. Yes, maybe -4 not being rotated. I have to do manually. Okay, what I want to explain from here. Let me log the. Okay. Okay, what I want to explain, I have to check some this slide also. So here I have completed, yes, this one. I hope I will make you understand, inshallah. Yes. Now we will maximize it. Yes. Okay, I told you that the maximum length of the shade which is available in the market is 4 meters. So actually we know the panel point. So panel point means that let me little bit show this sheet on this side also and also on this side. So we are computing the length of the sheet required between one panel. The length of the sheet required between one panel will be equal to P by cos theta plus E. E is the edge for for end cover. You can see that. So we are computing the length of the sheet required between one panel point. So it means that I have to use the n value equal to 1. If I computing this value and the answer is coming out to be 1.5 meter. So it means that the length, maximum length available is 4 meter. So I will check that how much length is required. I'm unable to select. For example, here, because I'm unable to, okay, so select. I'm unable to select this. Okay, anyhow, I will explain. I will check that whether I can cover this length between two conductive purlin with one sheet or not. So let's suppose I will compute the total length of the sheet that may cover two panels. So here I have to use the n value 2. N value 2 means that I want to determine the total inclined length of the sheet covered by one single length. So I will use the n value 2. So 2 means that 2 panels divided by cos theta plus E will be the length of the sheet covered between two panels. So if this distance is less than 4 meter or equal to 4 meter, then instead of using one small sheet, I will use one larger sheet to cover up the two consecutive panels. So in this case, I don't need to cut the sheet into smaller size. But if the length of the sheet required to cover the length between two panels is more than 4 meters, then it means that I cannot opt this option. This means that I need to use the maximum length according to the length between one panel. So in this way, we need to compute the length of the sheet required to cover the one panel, two panel, or three panels. So out of this option, we will select that whether we can use a single sheet to cover the two panels or not. Similarly, I have also explained if you are computing the length of the sheet required to cover one panel, n value is equal to 1, p value is very large, np over cos theta plus e. If this answer is coming out to be more than 4 meter mean that we cannot cover the spacing by one sheet. So for example, that option may be this one. It means that that is a 4 length, so there will be some of the gap left. So actually, we do not provide the end cover in between. So it means that to cover this, we need to provide the purlin at the center. That is not a good option because we always provide the end lap at above the purlin. So just to fill up this gap, we need to provide a purlin also here. If the purlin is directly placed on this top truss member, so that will be designed also as a beam. So we are not going for this option. So I was on this slide. So accordingly, the length of the sheet panel L is calculated corresponding to 1, 2, or 3 times the inclined panel length plus the required end length. So whatever will be the length, we will always round to the upper side in a multiple of 0.25 meter. If the required length of sheet corresponding to single panel length is more than 4 meters, or if the available section modulus does not satisfy the flexure criterion, we need to provide extra purlin to reduce the length of the sheet. So extra purlin in that case will be provided at the top of the top chord, between the top chord of the truss. So in that case, we need to design the top chord also as a beam or for the bending moment. So in that case, what we will do, we will provide the purlin in the center of the top member. So we will reduce the panel length into half. Just I have explained. And top chord of the truss must be checked for the combined action of the compression and bending, because load is not acting at the joint. Similarly, purlin design must also be made using spacing of the purlin equal to the modified center to center distance between purlin. So here I told you already that. So we always provide the end lab above the purlin. So where we need to provide the end lab, we need to provide the purlin. We never provide the end lab in the center, because in that case, if load is acting due to bending, the gap may open. So total load on the roof sheeting may be dead load of roofing, self weight of the roofing, insulation panel that we are directly attached with the roof sheets, plus live load. And live load will be the snow load. And we do not consider wind load to design the roof sheet. So we are not including the self weight of the purlin, because roof sheets are attached with the purlin. So weight of the roof sheet is transferred to the purlin. So no weight of the purlin is transferred to the roof sheet. So while we are designing, we are considering that the roof sheet, we always design the roof sheet for a unit length. Unit length means span of the truss, the roof sheet will be, we assuming the length, horizontal length between the purlin, and we are assuming that the width of the roof sheeting will be 1 meter. So while designing, we are considering that this is a beam which is having a unit width. The length of the sheet will be the length between the panel points. So load per unit length of the roofing, the total load is actually in Newton per meter square. So if we multiply the total load with 1, we are considering that total width of the roof sheet is equal to 1. Then we can convert into a UDL load for Newton per meter. So load per unit area of the roof multiplied by 1, then we will have the load per unit roof area. So magnitude wise, the unit will be Newton per meter. Then we will compute the total maximum moment which is being produced in the roof sheet. So omega is the total load or UDL load acting per unit area. So we need to use the panel length, because roof sheet is supported between the panel points. So we need to consider the horizontal distance which is perpendicular to the gravity direction. Omega p square by 8 will be the maximum moment against which the roof sheet is subjected. So section modulus required, we can compute multiplying the applied bending moment into 1000. Why? Because we want to convert into Newton into millimeter divided by allowable stress. So then we will try to select the section by using this table. So we will try to select a roof sheet which is having section modulus more than or equal to our required section modulus. So depending upon our required section modulus, we will select the suitable gauge of the sheet. And then we will check the self weight, because at the start we are assuming certain self weight of roof sheet. So for the selected roof sheet, a roof sheet that we have selected, for example, required section modulus was 6. into exponent 3. So this sheet is having the section modulus more than 6. So it means that that will be my first trial sheet. I will apply all the capacity check. For this sheet, the actual weight is 119.3. So I will check this actual weight against assumed self weight. For this purpose, we are multiplying the weight which is given in the table for the properties of roof sheeting by 1.35. Why we are increasing it by 1.35? Because in table the weight of the sheet is given corresponding to flat sheet, but actual sheet is having the corrugation, so due to the corrugation weight may be more. So we are assuming that the weight of the actual sheet is 35% more as compared to the flat sheet, and this weight should be less than equal to 1.2 times of the assumed self weight. If this check is satisfied, then our self weight check is okay. And at the end, we also check the deflection. So allowable deflection is span divided by 90 as specified by the code, and we compute the maximum deflection that may produce by the any appropriate formula. For simplest supportive condition, we determine the maximum or actual deflection by this formula, and the allowable deflection is given or specified the code by L by 90. Span by 90 mean that panel length divided by 90. So if actual deflection is less than allowable, so deflection check is also satisfied. Okay, at the end, we will need to compute that how many number of the sheets are required to cover our area for the roofing system. So we supposed to use this formula. So this formula represents the total area, inclined area that we need to cover by roof sheeting on the one side of truss. So this I will explain from this slide. Let's suppose that we are having this truss and we are also having this truss. So you assume that this there is 1, 2, 3, 4, and 5 trusses. So this is the total area between two trusses, inclined area between two trusses on one side. How I can compute this inclined area? This inclined area is equal to, if I know this half length of the truss, half length and this angle. So half length divided by this inclined length will be equal to cos theta. Or if I divide the half length by cos theta, I will have this inclined portion. But we also provide some projection of the sheet on this side. So this is the end projection that we need to add. So it means that if I know this length is equal to half length divided by cos theta plus E multiplied by the spacing between trusses or the length of the purlin. That will be this area. And then we are having how many in this area? 1, 2, 3, 4. If we are having 5 trusses, 1, 2, 3, 4, 5, then number of trusses minus 1 multiplied by the area between two trusses will be equal to total inclined area on the one side. And then we will multiply with 2 because we also need to cover the inclined area on the other side. So let me repeat the formula over here. So I will copy this formula on this slide just to explain. So I told you that we provide some extra inclined length on this side. So this inclined length will be equal to L by 2 plus edge projection half length divided by cos theta will be this inclined distance, multiply by s. If we are multiplying with the s here, then we will have this inclined cover area. And if we are multiplying with total number of trusses minus 1, 1, 2, 3, 4, 5. If we are having the 5 trusses, then we will have the 4 panel or 4 segment that we need to cover. So that will be total area on the one side. And if you multiply with 2, then we will have a total area on the other side. So that is the total area of roofing system on the one side of the truss that we want to cover up. So we need to compute this area. So I don't explain this formula, just this. So here, this is the total area that we have computed from the previous slide, and this CLE. So you can also write the A1. A1 means that effective area covered by one sheet, which is equal to C into L minus T. So one sheet is covering the area of this one. So total area divided by area, effective area covered by one sheet will be total number of the sheets required. So here we can compute the total number of the sheets required on the one side. And if we are multiplying with 2, then we will have the total number of the sheets that are required to cover the entire roofing system or roofing area. And then we are connecting this by JBoard, and we have to provide our result in following summary. So in the results, we have to highlight the 5 things: what gauge of the sheet we are using, what is the standard designation, what is the panel size of the sheet that we are using, what is the bolt spacing that we are using to connect the sheets along the length and along the sides, and how many number of the sheets are required. So I will stop here. So next time we will solving the example related with the roof sheet design. We will assume the actual data, and then we will compute that how many number of the sheets are required for our truss roofing system, and what will be the gauge value and the standard designation. So at the moment, if someone is having the question, he can ask me. Anybody who is having question, just raise the hand. Yes, Uzair, please ask the question.
सर जिधर वो हमने शीट का इफेक्टिव एरिया फाइंड किया जो एंड लैप और साइड लैप की वजह से हमने फार्मूला जो निकाला उसका, तो सर अगर हम वैसे ही मतलब शीट की लेंथ और विड्थ में से एंड लैप्स और साइड लैप्स को माइनस करके तो फिर उन दोनों को लेंथ विड्थ को मल्टीप्लाई करके निकालें, तो वो सेम आएगा या नहीं सेम आएगा फिर इस तरह से? इसको चेक करके देखो, कंप्यूट करके फिर तुम्हें आंसर मिल जाएगा. आई डोंट वांट टू कमेंट, इसलिए इसी वजह से मैंने समझाने के लिए वो पैनल 5 बनाए हैं. समझ लगी बात की? इसलिए वो बनाए. अगर कंप्यूट करके देखो थोड़ा सा फर्क आ जाएगा. ठीक है, ओके सर. यस, इसलिए एक्चुअल देखो बना के ना स्केच करके फिर देखो इसको. हमजा, यस, व्हाट इज द क्वेश्चन प्लीज? हाँ जी पूछो. एक मिनट, मैं आपको ट्रस्ट देख लेते हैं. Just wait for a minute. Yes, let me share these slides again. अच्छा, स्लाइड नजर आ रही है ये आपको? अच्छा, ये वाली स्लाइड थी. अच्छा, मैंने okay, I have explained to you that how you can compute the panel. Actually, panel length is the horizontal distance between two consecutive joints with reference to top chord. So panel length is this horizontal distance. This distance. Okay. I told you how to compute this joint. Okay. I told you that for the top chord,
if you know the length, total length of the top chord, divide it to 1, 2, 3, 4, 5 equal parts, then you will have this point. You understand? In the same way, total length, divide the total length into 1, 2, 3, 4, and 5 parts. So this is divided into 5 equal parts, bottom length. You understand me? यार ये मैं listen to me. What I spoke 5. I told you 5. Okay. I told you. Okay. 1, 2. This is not the member. Okay. This dash line just shown as a symmetry line of symmetry. So assume the bottom length is divided into 5 parts and top inclined length is divided into 5. Both are divided into 5. Yes. हाँ जी नहीं वो जब हम कुछ भी हो सकता है जब हम एग्जांपल सॉल्व करेंगे एक्सप्लेन कर दूंगा आई जस्ट एक्सप्लेन दैट if we are provided with the effective length that could be any value there then we can refer the or check the capacity from that table ठीक है I did not speak the word or haven't spoken the word total length. So effective length may be any length depending upon the total length and the K value. While we are solving some numerical, I will explain it again. Okay? Okay. So anybody else is having question? If you are not having the question, then I would like to conclude the lecture.